So, good day ladies and gentlemen. Today we'd like to introduce to you the Etheria, a revolutionary urban air mobility vehicle. Why is it revolutionary? It's revolutionary because we're one of the first people to implement hydrogen inside urban air mobility. You might wonder, what is urban air mobility? Urban air mobility is an efficient, fast and convenient airborne mode of transportation that utilizes cutting-edge technology like vertical takeoff or landing to increase the accessibility and reduce the barriers of urban transportation. To portray what this entails and what the logistics around urban air mobility is, we'll show you a short video. I'd like to stress from this video that vertiports are the transportation hubs of an urban air mobility network. They form the train station in public transit. In urban air mobility, we generally know three segments. The short range, which is below 50 kilometers. These are generally drone-like configurations. Then we have the mid-range. They fly up to 100 kilometers. An example is the Archer Midnight. And then finally, we have the long-range segment, which is where we have designed for as well. A current example is the Lilium jet. So, what is our design? Our design can be seen on the right, making a transitioning maneuver. We have a maximum takeoff weight of 2,520 kilograms, of which 510 kilograms is payload. This allows us to bring 4 passengers, plus a pilot, and also, of course, some luggage. We use hydrogen, specifically speaking, 360 liters of it, which translates to 9.6 kilograms. This gives us a range of 400 kilometers at a cruise speed of 300 kilometers per hour. So what makes us different from the current existing markets? The current standard is the Lilium jet. It flies 250 kilometers. If you draw circles of 300 kilometers around all the major cities in Europe, the black circles indicate all the cities that are currently isolated, meaning they can't be traveled to by any of the other major cities. What does Etheria change? Well, with 400 kilometers, we open up Europe. With 400 kilometers, we can now reach Paris, London, Milan, and Munich. Especially London and Paris are crucial cities to be able to reach. So we focus on an intercity basis. This brings us our main competitor, high-speed rail. So, how does Etheria compare to high-speed rail? To be able to portray this, we propose our main business case from Paris to London. This will be from La Défense in Paris, the largest business district in Europe, to Canary Wharf in London, the second largest business district. This will be split up in 3 main phases. The first mile, in transit, and last mile. First mile, meaning that an analogy in public transit would be from your door to the local bus station. The in-transit phase is the main mode of transportation. So this would be during the bus rides. And then the last mile is from your bus stop to your final destination. Moving on to the first mile. To be able to properly portray the first mile in UAM, we must choose a suitable location for our vertiports. We have chosen this location. This is based off of the fact that vertiports, or a UAM network, functions most efficiently when working with a few centralized locations in the city. We assumed that one of these centralized locations would be near La Défense, since it is the largest business district in Paris. Working from this, we get an 11 minutes travel time with 2 interchanges. Then the equivalent for the rail is 3 interchanges with a 23-minute travel time. As you can see, we already make an advantage currently. Then comes the biggest advantage, the in-transit phase. Since we have the same cruise speed, but we can travel in a straight line. We halve the time that the Eurostar takes to go from Paris to London. Moving on to the last mile, we again make the same assumption. There even has been an artist competition of making a vertiport near the water. This was the result of the winning architecture who made the design. So from this location, we can now, without any interchanges, reach our final destination, Canary Wharf, in 5 minutes. The rail arrives at King Cross Station, the main station in London. From here, it takes 31 minutes to reach your final destination with 2 interchanges. So, to summarize, the Etheria takes 2 hours in total to go from door to door, with only 4 interchanges. Note here that we added the time penalty, since any customs or delays might be present that we've not accounted for. The high-speed rail, however, still takes significantly longer, with 3 hours and 15 minutes. And, more importantly, 7 interchanges. So, what barriers have we tackled with the Etheria? We have interchanges, travel time, and service frequency. We have reduced the amount of interchanges, reduced the travel time, and increased service frequency by working on an on-demand basis. Now Carmelo will talk about why our design is smart, safe, and sustainable.
Thank you very much, Damien. So I will now discuss the qualitative characteristics of Etheria, which is a smart, safe, and sustainable approach towards UAM vehicles. So I will now discuss what makes Etheria smart, safe, and sustainable. Etheria, first, is smart because of its extended range of 400 kilometers. As Damien has already explained, it can connect 92% of Europe's top 50 cities by GDP. It is also more than any other eVTOL project in a similar stage of development. Additionally, its speed of 300 kilometers per hour at cruise, it is the highest as well for against any other eVTOL projects in a similar stage of development, as well as being competitive with high-speed rail. It is also smart because of its simple, effective, and innovative method of transitioning. It can take off with all 6 rotors pointing in vertical direction and then slowly tilt them forward to gain horizontal speed and become wingborne. It is smart because it has been designed in a multidisciplinary approach and design optimization, which has yielded the final design. We can see the inside of Etheria right now, and if we focus in the front, we can see the cabin, which has been designed like a business jet cabin. This ensures passenger comfort. And if we focus on the back, we can see the power system. We see the main characteristics are the hydrogen tank locations and the batteries which are stored in the wing, and the fuel cell which will convert the hydrogen to electricity. So next on, what makes Etheria safe? Etheria is safe because it has been designed with a fail-safe philosophy. This means that all its systems are redundant. It has the highest grade handling qualities as well as a robust controller design. This means that a pilot with any level of skill can pilot it. Additionally, it has been designed for stability at any, not at any, but at extreme wind conditions. Those can be such as 30 km per hour crosswind and 30 km per hour vertical gusts, as well as being all of that under one engine in operative conditions. It is to be noted that Etheria has 2 engines per propeller, so the one engine in operative condition limits the maximum thrust of one of the propellers to 50% of the original condition. Lastly, if vertical landing was not feasible due to weather conditions, for example, it has also been designed for the possibility of doing horizontal landing. However, if everything crumbles, it has also been designed for crashworthiness. This means that in the case that it crashes with a velocity of 9.1 meters per second, that is the velocity at which 95% of all helicopter crashes occur, it will ensure passenger survivability. This has been done thanks to a compressible crash floor. The compressible crash floor will absorb the impact energy and sufficient post-crash cabin space, as well as a firewall to prevent fire from spreading into the cabin. Regarding the sufficient post-crash cabin space, this has been analyzed by using the crash diameter coefficient. So the dangers of hydrogen are flammability, explosiveness, and potential leakages. The use of hydrogen in aviation is a very sensitive topic, I would say, because of these issues. So we have to ensure that the hydrogen is stored in a safe manner and will not cause any problems for the passengers nor for the surroundings. So to ensure that the tank is not damaged in a crash event, we use, as said, the crash diameter coefficient, which is it's a method to determine what the diameter of the area of the fuselage is after the event of a crash. We can see it, for example, in the red circle in here. That would be the diameter of the fuselage after a crash, versus the blue circle, which would be before the crash, of course. So what we've done is to place the hydrogen, which can be found in here. If this is etheria, and we look at it from the back, we see that there is a red box, which corresponds to this intact volume, and that's where the hydrogen storage is placed to ensure its safety. Lastly, I would like to talk about what makes etheria sustainable. Etheria is sustainable because it has been designed with the most technologically advanced materials, which make sure that it is strong and light. The light material yields a light structure, which yields less fuel consumption, as well as the fact of using hydrogen to power etheria as the main energy source makes etheria not have any other emissions into the environment other than water vapor. Etheria is sustainable because it is expected to be launched into the market in 2030, and Airbus has already said that they expect that by 2025 they will recycle 95% of its composites. So Etheria is also expecting to recycle a large majority, if not all, of the materials used in it. Lastly, it is sustainable because no new infrastructure is needed for it to fly. Etheria can land in most of the helipads in the world, and the hydrogen availability is not an issue, as it is expected that all major cities and major airports in the world will allow for hydrogen refueling. An example of this is the Shell building the biggest hydrogen refueling station in the world in Rotterdam as of right now. I would also like to dive a bit deeper into the technical parameters of Etheria. We will first see the mission profile. Etheria takes off vertically, then it transitions into horizontal mode for climbing, where it will climb up to 2,400 meters. This is to ensure passenger comfort in a non-pressurized cabin. It will then descend, and once it reaches its target altitude of 30 meters, it will transition to vertical flight mode once again to land in a vertical manner. It is to be noted that Etheria will be in vertical flight mode for only about 1.5 minutes of the entire mission profile. That accounts for the transition from vertical to horizontal mode and the transition from horizontal to vertical mode. And this is because EASA's regulations, so the airworthiness regulations, only require the Etheria to hover up to 30 meters before transition occurs. We can see the power demand in each of the phases. It is extremely high during the vertical operation of Etheria, and this leads the design of the power needed and the power requirements. But since it is for only a short period of time, it will not lead the energy requirements, which will more likely be led by the cruise condition, which can last for longer than 1 hour. Regarding the noise, It is taken at a distance of 30 meters, as Etheria is an urban air mobility vehicle, and it is then assumed that people will be very close to it while it's taking off. The noise during takeoff is only 80 decibels. That is comparable to a washing machine and is over 1,000 times less than current helicopters. And during cruise, when analyzed from 2,400 meters, the perceived noise of Etheria will be only 34 decibels, which is comparable to a quiet whisper or a silent library. Regarding the power system, it has been designed hybridly. So during hovering, since it is a power expensive maneuver, it will be done by batteries and fuel cells primarily. This is because they can provide high power. And during cruise, since it is an energy expensive operation, that will be performed by hydrogen, which has a very low energy density. The hydrogen used is 9.6 kilograms only. However, the tank mass is of 167 kilograms. That is a lot. However, when we design Etheria with only batteries, we would find out that it would weigh 4 times as much. So that is actually great news. Additionally, the fuel cell, so the system that converts hydrogen to electricity, weighs 42 kilograms. The battery needed to supply the required power would weigh 205 kilograms, amounting to a total power system weight of 510 kilograms, which is much less of that of Joby, which would be a direct competitor in the eVTOL market. Now, I would like to hand it off to Damien again to perform the financial study.
So, maybe more importantly, how does this all translate to your wallet? The unit price cost of the Etheria will lie around $2 million. The total development costs, so this is our salaries or any costs that are related to research, will amount to $113 million. With a production cost of $930,000, we need 106 units to break even. This will give us a return of investment of 14%. But the potential does not stop here. Our current competitor, another competitor, is Lilium. Lilium sells their eVTOL at $2.5 million. So if we would increase our selling price to the same price as Lilium, we would have a break-even unit of 78 and a return of investment of 118%. But these are all nice figures and numbers, but what does it mean for the passenger, the user, which is you? A train ticket currently from Paris to London will cost you about 90 euros. However, this is not from point to point and less fast than the Etheria. The plane will cost you 65 euros. This is also less fast as it doesn't bring you from point to point. So what does the Etheria cost? It will cost you 94 euros per person. This is based off of our yearly operational cost of $330,000. So, this was our presentation, and we hope you'll fly with us soon. I'd like now to invite the rest of the team to answer our questions. Yes, please.
Okay, so very interesting concepts. Bring people on a very specific route. So I have two questions, maybe a little bit unrelated. One is around the, let's say it's a sustainability angle here. You already have a train which can bring thousands of people potentially from one place to another, and then you have this vehicle which can bring 5 people. So if you can talk a little bit about that. So that's one piece. The other is, you talked about a robust controller design, high-grade handling. If you could talk a little bit more about how you arrived at that conclusion.
Yes. So I'll just repeat the question for the rest of the audience. At one point in the safe section, we discussed military-grade handling and high-performance handling and a robust controller. So what does this mean and how did we come to this conclusion? I'll hand it off to the stability department to answer this question, which is Carmelo and Barkin.
So thank you for your question. In regards to the robust controller, in control system design, we can make the design such that the controllers have a sufficient contingency in terms of gain and phase, as we call it, so that the control system does not destabilize the aircraft. In terms of robustness, other than that, we have, like, the control system is designed such that we are avoiding pilot-induced oscillation during flight. This was something we paid a lot of attention to, which means that even pilots with relatively low skill abilities will be able to fly this aircraft. In addition, aircraft have, as we call it, dynamic motions, and these need to be damped. We damp these oscillations in the aircraft way more than that is required by the air safety authorities. In fact, they are damped so well that if this aircraft were to be used in a military operation, not to say that that is the case, it would be. So we are meeting much more stringent handling quality criteria than what would be necessary to actually certify this aircraft.
Second question?
Yes. Sorry, did it
Sustainability of comparing a vehicle with 5 people versus a train with...
Yes, exactly. First off, did it answer your question correctly?
Yeah, yeah.
Okay, great. So concerning the second question, how do we compare it to trains? So, for example, now currently, a taxi service still exists, even though most cities in the Netherlands, for example, are connected by trains. So we want to replace that market, because obviously planes cannot compete with the capacity of a train. However, some people still either do not want to take public transit, or they travel so much that they want to make use of this decreased travel time. So to make sure that all people are traveling in a sustainable manner, we want to able to provide that opportunity to them. But obviously, we would work in sync with the trains, because the capacity of trains is still, it's great, and we cannot compare ourselves to them. Does that answer your question? Great.
Hello, you had a question.
Yes, please. Concerning the eVTOLs, there is a big concern about the lithium battery thermal runaway following a crash landing. Did you consider this condition?
So I'll just repeat the question for the rest of the audience. So as everyone knows, electric cars, they also burn up. So after we had a crash landing, it could happen for us. So how do we take into account for that? I'll hand it off to the power department, since they made the decision of the battery positioning.
Yes, so the question is, after that we handle how do we ensure that thermal runaway does not occur after a crash? So the main reason that we place the batteries in the wing is that if a thermal runaway would occur, that we would have sufficient space towards the hydrogen subsystem that it would not cause an explosion for the hydrogen. In that sense, we took that into consideration. Did that answer your question?
Thank you very much for your presentation. As the title of your project was the crashworthiness, you emphasized very much on from the inside. Did you consider the risk to the environment as you are now taking off from the vertical to the horizontal phase in a very populated area? And we all know that in eVTOL that phase is very critical. So what about the effect of a crash in that situation? Did you
Yes.
consider it?
So I'll repeat the question. We discussed about protecting the passengers, but how do we protect the environment from the eVTOL? So, correct? So by protecting the passengers, so preventing a post-crash fire, we immediately also protect the environment by not causing an explosion, since the major concern would be for the hydrogen tank to rupture and cause an explosion. And secondly, part of this safety to the environment is also imposed by regulations and vertiport locations. And of course, also the robust controller design contributes to the safety to the environment by not crashing in the first place. But if we do, and it would be close to a populated area, we would ensure no explosion or any gas leaks by having this safe crash area and ensuring that nothing will happen to it. Does that answer your question?
Yes, I have a question about redundancy, because you mentioned that you took redundancy into account, but let's put it this way, how many propellers can you lose before you are in a situation where you can fly anymore? And especially during a vertical takeoff landing, I can imagine if you have two propellers on one side not working anymore, it might flip over, for example. What do you say on that?
Yeah, I'll just repeat the question for the rest of the audience. So what happens if we lose an engine or propeller, and how do we ensure that we do not flip over? This is a question for the stability department.
Thank you for your question. So regarding vertical flight, the aircraft is deemed stable and controllable under extreme wind conditions, as explained, of over 30 km/h crosswind and vertical gusts, and with one of the two engines in a rotor inoperative. So that would be that one of the rotors would have a maximum available thrust of 50% of its original condition. This has allowed us, using a method that is discussed in a report, to ensure that the aircraft is stable and controllable during vertical flight. If, however, we lose a propeller, the aircraft becomes uncontrollable during vertical flight, and it is that reason why we have designed as well for a horizontal landing possibility. We have done a research that shows that the main reason for propeller losses are because of bird strikes, and those are extremely unlikely to occur below 1,000 feet of altitude, and also while the horizontal velocity is of 0, and hence it is decided that the assumption holds that during the vertical takeoff, no bird strike will occur, and all propellers will work accordingly. And in the case that we damage a propeller during horizontal flight, we can still land horizontally. Since the propulsion is also sized for hover conditions, it has a big surplus of thrust capabilities, so it can land horizontally and be controllable and stable under multiple propeller failures. Does this answer your question?
Yes, thanks.
Up there.
Yeah, thank you very much. Like the presentation is super nice, the animations and stuff. I have a question for the power supply people. Like, what kind of assumptions did you guys take into consideration while actually designing the power system? Because usually during takeoff, the fuel cell systems, you also mentioned Degen, they didn't till now. They still have some problems to actually provide takeoff power to their aircraft. So, what kind of assumptions did you take?
Go ahead.
Yes, so I will repeat the question for the audience that's following online. So the question is, what kind of assumptions did you make to be able to deliver power during the hovering phase of our aircraft eVTOL? So the main way that we did the cooling of the battery and the fuel cell is that we use radiators or heat exchangers, and on those heat exchangers we place a fan, which makes sure that we get sufficient airflow through the radiators, even still when we're flying or just hovering, and don't have airspeed, so natural airflow going through the radiators.
Yeah, but my question was about actually the fuel cell power density.
Oh,
Did you consider efficiency, for example? I was waiting for like.
oh yeah, so we've taken into account, talking about the efficiency of the fuel cells, we've taken into account the efficiency of the fuel cell, so we've used an off-the-shelf fuel cell, and it has written down the efficiency of the fuel cell, so we've taken that into account with the power density in order to be able to provide sufficient power during hovering. Did that answer your question?
Yeah. We have time for one more question. Can I ask another one? Yeah, sure.
Go ahead.
Can you better specify how did you size, did you dimension the subfloor for crash landing?
So I will just repeat the question. So we mentioned in the presentation that we have a crash floor structure to protect the passenger from any too significant loads that could injure the passengers. So to discuss this, I'll give the microphone to Jorik, who sized the crash floor structure.
Yes, so thank you for your question. Well, it's not possible to fully simulate a crash or a crash floor. We decided to make a simplified model of only a crash where it lands, or like it crashes vertically with an impact velocity of 9.1 meters per second, as specified before. And we modeled the stress-strain curve of a honeycomb structure that is placed under the floor, and then we calculated the acceleration during the whole crash and made sure that this was sufficient with the regulations. Does that answer?
Acceleration of the rigid body of the aircraft, or the floor.
Yeah, so the floor. So the floor will deform completely during this crash, so it will not be intact anymore, but it will absorb all the energy, all the kinetic energy that the aircraft has.
Slide for that?
Yeah, we do, I think. It was 23 centimeters. Here you can see the yellow part under the cabin.
Yes, this part.
Does that answer your question? Thank you.
Thank you very much.